Hello and welcome to another overview video. We're looking at Module 7. We continue looking at second order linear differential equations. And going to kind of build off of what we did in Module 6, where our main focus in Module 6 was this second order linear constant coefficient homogeneous ODE. And you recall that the ODE led to a characteristic equation where the coefficients of that quadratic equation were the same as the coefficients from the ODE. Solving that quadratic equation allows us to find the general solution, where if we get two real solutions, R1 and R2, then our two solutions were e to the R1x and e to the R2x. And then we had our two unknown constants, C1 and C2, where we multiply y1 and y2 by those. What we'd like to do in Module 7 is now consider the corresponding non-homogeneous case, where the right-hand side of the ODE goes from 0 to being some non-zero forcing function f of x. So the general solution will still involve the fundamental set of solutions, y1 and y2, which solve the homogeneous case, but we'll now need a third term denoted y subscript p, also called the particular solution. And the particular solution will go into the differential equation to result with that forcing function. Some alternate notation, you might see this written as a capital Y for the particular solution. Now, the form of the particular solution is chosen based on the form of the forcing function. So in general, the forcing function will tell us how to form our particular solution. And if we have a exponential or a trig function, the constants inside the argument won't actually change. Notice the lowercase letters there staying the same, but rather the coefficients out front are what changes. So in the particular solution, these capital letters are the undetermined coefficients, and we would put the particular solution in with these undetermined coefficients and take derivatives and substitute it into the ODE, and then we would solve for those undetermined coefficients. And that method is a little advanced and it's broken into two methodologies in this module. All right, so let's try out using this table. Again, based on the right-hand side forcing function, you identify a similar function and then find the corresponding particular solution format where the capital letters are the undetermined coefficients. So here's an example of a second-order linear constant coefficient non-homogeneous ODE. We got our forcing function, negative 200 sine of 2t. See if you can figure out the form of the particular solution. If you need a little more time, go ahead and pause the video now. So based on it being a sine function, you might posit that it is undetermined coefficient a times sine of 2t. So again, we're going to take derivatives and substitute it into the left side and then try to make it balance with the right side. So the derivative of sine is cosine. Notice that that 2 in the argument does not change when we take derivatives. But what it does do is comes out front and multiplies with that undetermined coefficient a. So there's the first derivative of the particular solution. For a second derivative, derivative of cosine is negative sine. We're going to get another 2 to give us negative 4a back to sine. So you'll notice that the 2 in the argument doesn't change, and therefore, when you see that number in there, you can use that in your particular solution. There's no need for undetermined coefficient in the argument. Same with the coefficient in the exponent of a base e exponential. Now you also notice that if I were to substitute these in, the 4y and y double prime could add up to the term on the right because they're all sine of 2t. And with the right choice of a, I could get that equation to balance. However, I would still have this term in the middle that has a cosine. And you notice there's no cosine on the right side. So because of the way, we take derivatives of sine and cosine kind of bounce back and forth, if you have just one of them in your forcing function, you need both of them in the particular solution to kind of balance out with this. So if I also had a cosine, a b cosine 2t, then the choice of b would allow the cosine terms to add up to 0. So we do, in fact, need the cosine term in the particular solution. So the correct answer is C. A sine 2t plus B cosine 2t. Going back to the table, you can see this corresponds to the row here, A sine bx, where A was negative 200 and B was 2. So we use that 2 in the arguments of both the sine and cosine. The negative 200 is going to be used for solving for capital A and capital B, but doesn't appear explicitly in the particular solution. Now, one thing that comes up when we do some of these problems is we get a little bit of linear dependence sometimes between the fundamental set of solutions y1 and y2 and the particular solution yp. Consider this example. Y double prime minus 5y prime plus 4y equals 4e to the t. Based on the form of that forcing function, it's a constant times e to the t. You would use the table and say the particular solution is a constant times e to the t. And I figure out what a is based on substituting that in. The problem is, if you were to solve the homogeneous case, which we know how to do that, that's actually not that hard to do, right? Go to the characteristic equation, and then that actually factors, and you get R1 equals 4 and R2 equals 1. And so Y1 is e to the 4t, and Y2 is e to the t. And then what you realize is that we have linear dependence between these two, right? If I were to divide those, I would actually get a constant, a over c2. And if we did the Wronskian, it would be 0. So we don't want that. We want the particular solution to be linearly independent from y1 and y2 for the same reason we want y1 and y2 to be linearly independent from each other. And so what do? Well, it's the same trick we used before. You remember that in the case when R1 equaled R2, y1 was e to the RT, and we would get y2 to be linearly independent by multiplying by t, right? So we do the same thing here, where we multiply by t to get the particular solution to be a t e to the t. And in general, you can basically just think that that polynomial coefficient is going to go up 1 degree when this happens. All right, now the other method we're looking at in this module is variation of parameters. And this isn't restricted to the constant coefficient case. So we now allow these coefficient functions to be varying functions of x, though they're usually just binomials, pretty simple polynomials. And if y1 and y2 are still the fundamental set of solutions for the homogeneous form, we pose the particular solution as u1y1 plus u2y2. Now, doing that by itself leads to it being very difficult to solve. If we were to take a derivative of that, we'd use the product rule on each of those terms and get those four terms there. And if we were to take the second derivative and use the product rule on those four terms, we get these six terms because you get sort of a repeated term there. If you were to substitute all these in to the differential equation and try to solve, you wouldn't be able to solve because there's just too many unknowns. In particular, the second derivatives here are problematic, u1 double prime and u2 double prime. And so the way to get rid of those is really cut them off right here. If we were to take u1 prime y1 and u2 prime y2 and say that those add up to 0, then we would only have the other two remaining terms, and we would get a much simpler second derivative that doesn't have u1 double prime and u2 double prime, and would actually allow us to solve for u1 prime and u2 prime. So that's the basis for it. You kind of restrict the format of the particular solution, but it allows you to solve for u1 and u2. All right, so same form for the particular solution, u1 y1 plus u2 y2, but we're now going to put on this requirement that u1 prime y1 plus u2 prime y2 equals 0. When you do that, your first derivative is much simpler because two of those terms are gone. So now y1, yp prime is u1 y1 prime plus u2 y2 prime. And that makes our second derivative much simpler, though we do need to use the product rule twice, and we do get these four terms. All right, so what happens if we put those in? So let's see if we can get this here. P0, u1 prime, y1 prime, plus u1, y1. So that's putting the second derivative in the first term, and then put in the first derivative, and then put in the function itself. And remember that y1 and y2 solve the homogeneous form, which means that p0 y1 double prime plus p1 y1 prime plus p2 y1 equals 0. And same for y2. Because y1 and y2 are solutions to the homogeneous form. And so what you can do is you can actually rearrange and get these things to appear. I guess I should have used another color for that. Let's use another color for that one. So you can get if you distribute, we can get P0 times U1, Y1 double prime, and then P1 times U1, Y1 prime, and then P2 times U1, Y1. And that will give you U1. All those terms have U1. P0 prime plus P1 prime plus P2y1. So when you factor off the U1 on those three terms, you actually get that property that y1 is a solution of the homogeneous form, and boom, it's gone. That's all 0. All right. And the same thing will happen with the y2 terms. So you get that one, and that one, and that one. Here you're factoring the U2. All those terms have a U2. P0, Y2 double prime, P1, Y2 prime, P2, Y2. And so that gives you 0 as well. All right, so what's actually left here? Notice that the P1 and P2 stuff is all gone. And so all that's left is these terms. So P0, U1 prime, Y1 prime, plus U2 prime, Y2 prime. Now, the way this is usually written is you divide through by P0. In fact, some people will just divide through by P0 at the very beginning, and they'll even call f of x the f of x divided by P0, depending on the book and the person. So you'll be a little careful when you go to different resources for this, but it's the same idea that this is the other requirement. Remember, in a specific problem, we know f of x, we know P0, P1, P2, and we would know y1 and y2. We're just trying to find u1 and u2. So this ends up being the second formula. So the variation of parameters method, it kind of starts off with this idea that the particular solution is u1, y1 plus u2, y2. But at its core, it's solving this system of equations for u1 prime and u2 prime. Now, it'll appear like a nonlinear system, but in terms of the variables being u1 prime and u2 prime, it is a linear system. You have these coefficients that aren't constants. So you can even set up a matrix and use linear algebra if you've learned that. But we'll just approach it as like a pre-calculus kind of system of equations. So we'll solve that for u1 prime and u2 prime, and then you integrate and find u1 and u2, and then you've got your particular solution. So we don't go through this derivation every time, but I wanted you to see this once, so when you get to the methodology, you know where those formulas are coming from. All right, so this is actually what you might get from those two formulas. In this case, y1 is x, and y2 is x cubed, right? And so y1 prime is 1, and y2 prime is 3x squared. And so you see those coefficient functions there. But when you look at it, it looks very much like a complicated nonlinear system, because when you're taught to solve for systems, you're thinking x is what we're solving for, but we're actually solving for u1 prime and u2 prime. And so if you just look at those as the variables and everything else as just stuff, it is actually a linear system for u1 prime and u2 prime. So if you want to take a minute and try to solve that using techniques of substitution, addition/elimination method, or even a matrix, go ahead and do that and see if you can come up with u1 prime and u2 prime. All right, go ahead and pause it if you need more time, which you probably do if you're actually doing this. I just don't want other people to have to wait. So I will check for the addition method, but if it's not super obvious, I mean, actually, it is not that bad to do either method here. So you could do the addition method or the substitution. I tend to go for substitution. And so that's what I'll show you here. And so with substitution method, I'm going to solve the simpler equation, which is the top one for u1. So we're going to subtract the u2 prime x cubed to the other side. So it's negative. And then we're going to divide both sides by x. And then those x's combine, and we get x squared. All right, and then the basis with substitution method is you would take that and you would substitute it into the other equation for u1 prime. So it goes right there. Right, notice now we have an equation where it's only u2 prime and we can solve for u2 prime. These are on the left are actually like terms. It's 3u2 prime x squared minus u2 prime x squared. And so those would actually combine and just give you 2 u2 prime x squared. You can divide both sides by 2x squared and get u2 prime equals sine of x. So you could then integrate and find u2 prime. Before you integrate, you do want to find u1 prime. And so then we take this and we substitute it back up here. And so u1 prime equals negative sine of x times x squared. And that's a harder integral to do, but it's still one that can be done. And you could integrate to get u1. All right, so rest of that's all covered in the methodology for variation of parameters. That's going to do it for this overview video. As always, we would like to thank Liam Trench for the textbook Elementary Differential Equations of Boundary Value Problems that we have used for images and text in this presentation. And that textbook is CC by NCSA. Thank you very much. I'll see you in the next video.